you pronounce, I will tell you.
Sarira Sahu.
Perfect. Okay.
Thank you. Thank you. Okay. So we are online now. So I will start.
Just 1 second. Okay.
Yeah, sure. Okay.
Okay.
¿Qué tal? Buenas tardes. Una vez más, les damos la bienvenida de parte de toda la Asociación Estudiantil de Ingeniería Física a una sesión más del Coloquio de Tesis e Investigación. El día de hoy tenemos a un invitado muy especial. Tenemos al doctor Sarira Sahu del Instituto de Ciencias Nucleares de la UNAM. El doctor dará su conferencia en inglés, así que a partir de ahora procedo a darles una presentación de él en inglés. También cabe recalcar que aunque la conferencia será en inglés, el doctor sí comprende español, así que si desean hacer alguna pregunta en español, pueden hacerla tanto en español como en inglés, y nosotros se la haremos llegar. Hello to all viewers. Today we have as a guest Professor Sarira Sahu from the Institute of Nuclear Sciences, UNAM. He earned his PhD in nuclear physics in 1994 at the Institute of Physics of Utkal University in India. He has been a postdoctoral fellow at the University of Valencia in Spain, at the Physical Research Laboratory, Ahmedabad, India, and at the Institute of Plasma Research in Gandhinagar, India. He joined the UNAM Institute of Nuclear Sciences in 1999. His area of research is astroparticle physics, including neutrino physics, physics of high-energy gamma rays, gamma ray bursts, and finite temperature field theory. He has more than 60 publications in international journals. In this talk, he will explain the observation of high-energy gamma rays and neutrinos from Blazars and their production mechanisms. So without further ado, Professor Sahu, the floor is yours.
Okay, thank you very much. Thank you for your kind introduction. And now you can see my screen. Hello. Can you see the screen?
Yes. Yes.
Okay. So I'm talking on something probably I don't know whether many people know or not. The title of my talk is Multi-TeV. Very active recently, and in fact, if you see in particle physics and high energy physics, a lot of experiments are being going on in these fields, and also theoretically a lot of work is going on, but unfortunately in Mexico there is not many people working on this one. So this is something interesting, very interesting, and it will be, I believe it will be interesting for you to listen to this talk, and maybe you will learn something. But in the meantime, let me tell you, if you have questions, so please write that, and at the end of my seminar, so you can ask me, okay? So my talk is basically, I will talk about the outline, what it is telling. I will tell what is a Blazar and what is multi-TeV flaring from these objects, and what are the recent modelings of this one, because we don't know, these are the objects which are millions of light years away from us, and we do get signal from them, but we don't know what are the mechanisms, so one has to use the known physics to model these things, and so I will talk about that one. Then I will talk, because the last few years, myself and with my students and some of my collaborators, I have developed a model where we have tried to explain all the flaring events from these Blazars, and we were able to explain a lot of them extremely well. So that is what I am going to talk about. Now, apart from that, now the interesting thing is that in the universe, there are a lot of particles with extremely high energy coming from, we don't know from where they are coming. They are coming from either from our galaxies or out of our galaxies, which I am going to talk about. And one of them is the neutrino, which is the most devil particle in the nature. And if we understand the nature of this particle very well, we will understand the creation of this universe much better. Okay, so which I am going to talk about and how it is detected and what are the recent works. Then I will summarize my talk. Well, it can go for longer. If you want, I can talk much longer. So I have a lot of material. Okay, now what is a Blazar? Blazar is a active galactic nuclei. Now, what is active galactic nuclei? Active galactic nuclei, you can tell that suppose our galaxy is the Milky Way. In the center of the galaxies, there is a supermassive black hole. Supermassive in the sense that it is a black hole of the size of 1 million or more than 1 million times the mass of the sun, which you can see in this figure in the right hand. So from where these jet-like structures are coming. So this central region is the black hole. And normally when you have the black hole, it will start eating all the objects which is nearby. Basically, this is called the accretion. So matter will go into this one and it will eat up. Once it is eating up, this will produce some jets. So now these jets, which are coming in both sides, now one can ask this question, well, if black hole eats everything, even light cannot come out, then how do you see this one? Well, this is the jet which is coming from a certain distance beyond which nothing will come out. So this is called beyond the horizon to this side. This is the one jet is producing. Beyond that, in the other side, towards the black hole side, when it goes, so nothing will come out. So this is the one which is towards this height of the event horizon where this jet is being produced. So this is the one where a lot of materials will extremely high energy, high speed, whatever you tell, it is an extreme condition. And this will be this jet. This jet is size of our, bigger than the solar system size. So these are enormous jets which are coming, okay? And they are producing all sorts of energy. And fortunately, if this comes towards us, then we will be able to see the variation in these energies, even in terms of minutes, okay? Minutes variation we can see. So these are the massive central black hole where matter is going into this one, these arrows which you can see. These are millions of stars, planets, whatever you tell. It is like Milky Way. It's just going, it is eating. So even in our galaxies, a few million years or maybe even more than that, this black hole will eat us, okay? So whole our solar system will go into that one, okay? Okay, so now, there are classifications of this one, this active galactic nuclei, where you see there are so many classifications, and I don't want to go into details of this one. And the one which is there in the right-hand side, HBL, high energy blazars, this is the one which we are going to study. Now question is that why do you want to study this one? So you see, first of all, this is a Blazar which is less than 5% of the regions, and then it comes the HBF, okay? So this is the object. Well, I mean, probably in next one, I will show you. Okay, it doesn't matter. Okay, this is the high energy Blazars. These are the objects which are extremely powerful. Extremely powerful means extremely powerful in all electromagnetic spectrum, starting from infrared up to the gamma rays, very extremely high energy. So they are producing this. And we can see that basically what happens is that, well, I mean, let me show. So these are different type of Blazars or active galactic nuclei. And the one which we are going to study is this little blue color, the second from the down, which is the one that is what we are going to study. Okay, this is something very interesting, which why I am going to tell this one now. Now, if you see these pictures, Blazars, how do you identify that? You see, this is the object which is a central black hole is eating all these things. And these are two jets which are perpendicular to the black hole, this disk. And the one which is, it is written Blazar, is the one when this cone is coming towards us and we are within the cone. Well, they are millions of light years away from us. So even if we are within the cone, it is not going to harm any of us. But we can detect very high energy particles here. So if we are within this cone, then this is called Blazar. If there is a big angle, suppose you are sitting somewhere else here, you said this is called quasars. And if you are almost 90 degrees to this one, then this is called radio galaxies. So basically, this is the same object, but it depends on where you are. Whether you are here, it is called Blazar. If you are here, it is called quasars. If you are here, this is called radio galaxies. Because you see, if you are in this cone, then you will see any change in this one will be directly, you will be able to see. On the other hand, if you are in an angle something like more than 40 to 50 degrees, then many things will not come to you. And if you are here, even lesser things will come to you. So it depends on where you are. So depending on your position from this perpendicular line, it is classified into Blazar, quasars, radio galaxies, etc. Now, so what are the specifications of this one? These are non-thermal spectra. So this produces normally non-thermal spectra. I showed you these are the two peaks. Normally you see everywhere, you will see two peaks. One is this one, another is this one. This is low energy peak. This is high energy peak. These are the flux, okay, or luminosity, whatever you see. And this is the energy. So in these energies, so this is the low energy peak. This is the high energy peak, okay. Now, why do we study these one? Well, these are the laboratories in nature which can produce extremely high energy particles. Extremely high means really high, which is unthinkable with the present technology on Earth. We cannot produce this, okay? So probably I have some slides where I can show you about how much size we need. So these are non-thermal spectra. Non-thermal spectra is basically, probably you might have studied what is the thermal spectrum, Stephens-Boltzmann law, where if you have a peak like this is called the thermal spectra, okay, thermal spectra. But these are non-thermal spectra in the sense that something is forced. It is like boiling water in a pressure cooker. You are forcing that, okay, forcing to boil. It is not the natural way of boiling. So like that, or you are kicking a football, it is not the natural way. You are just kicking. So that is a thermal spectra. No, sorry, non-thermal spectra. So that is the way it comes, because this is a system where so much violent process is going on. Millions of stars, energy is coming out in minutes, seconds. So it is really terribly powerful systems where things are forced to do that. And that is called the non-thermal spectra, their spectrum. And rapid variability across the entire electromagnetic spectrum. So because of this non-thermal process, the spectrum which are produced are across the electromagnetic spectrum, starting from low energy to extremely high energy gamma rays. So they are producing that one. And these are the system in nature where relativistic effect can be seen, okay? They are producing energy in a scale enormous, the velocity in a scale enormous, and everything is in extreme, okay? So that is where you can have a bulk motion in relativistic speed, okay? Then small viewing angle, because this angle is not very big, it is very small. So although this cone, when it comes to us, it is very big, but it is a very small angle, okay? Boosting of emitted power because of the relativistic motions, relativistic effect, your energy will be boosted, which is not there in classical physics, okay? And then time scale will be also shortened, because you see in relativity, when your travel speed is close to the speed of light, then your time scale becomes shorter. Like for example, if you go around this black hole, the time will be very slow. Your watch will be very slow, like that, okay? Okay. Then why do we study these things? Well, we really don't understand many things about this object. One thing is that energy extraction mechanism from the central supermassive black hole, how the energy is being extracted in these jets. So these mechanisms we have to study. Physical properties of the astrophysical jets. So these are called jets. These two are called jets. And what are the real properties of these jets? Because if we don't understand these, then we don't understand how the particle comes, how the energy is being extracted from these objects. So we don't understand that. So one has to understand that. Then acceleration of charged particles. Now on Earth we see extremely high energy particles. So we have detectors on Earth, so we see them, but we have no idea how to produce them in Earth because we have absolutely no technology, no science, so we cannot produce them. So we have to depend on the nature. So then we have to study that how the particles are being accelerated. One has to study that both theoretically and experimentally and observationally also. Then production of ultra high energy cosmic rays, very high energy neutrinos, multi-tera electron volt gamma rays, etc. Because these particles are very related. So if we want to understand the nature of the universe, that is most important. Okay, so then one has to understand this one. Then there is another one called constant in the extragalactic background light, or EBL. What is this one? You see, you probably know that when the universe was born, after the Big Bang, after something around 80,000 years after that, the protons, electrons, and light, they started separating each other, and protons combined with electrons to form hydrogen atom. After that, this light became decoupled, just simply left this atom, hydrogen atom, and it went freely. But during that time, the whole universe was expanding. And then what happened is that when the universe was expanding, so this photon get cooled down. And now this photon is now, it is very cool, and it is a perfectly small spectrum, which has a temperature 2.7 degree Kelvin. So this is called the cosmic microwave background. After the 80,000 years of the creation of the universe, after another few thousand years, when the galaxies formation took place, so when these galaxies were forming, that time nuclear, because of the nuclear reaction, lot of light formed. These lights, like in sun, we have the nuclear reactions, so this light is coming, what we see. Though this type of light was coming, but this type of light were everywhere in the universe, so they became a background. Well, this light, little higher light, little lower light, so these lights were generated from here, and they became a background. They became the one where everywhere they were there, they are there. So they formed a background that is called extragalactic background light. Now, this is very important point because this is the one which really blocks a lot of things coming to the Earth or coming to our experimental, telescopes. So if a very high energy gamma rays is coming from very far away, it may not come because of this one, because it will interact with this background light and produce electron-positron pair. Then we will not be able to see high energy gamma rays from far away objects. So this is the one, because we are talking about these blazars are quite far. So their gamma rays, tera electron gamma rays will suffer from this attenuation because of the extragalactic background light. So we may not be able to see them, or even if they are coming, they will be depleted, attenuated because of this background. So when you are doing any modeling, you have to take care of this one properly. Okay? All right. Now, let's come to this, the spectrum, whatever we see. If you see the flux of luminosity, as I told you, there are two peaks. One is the first peak called synchrotron peak. Another is called the inverse compton or self-synchrotron peak, SSC peak. So this happens, this first peak happens. What happens is that in the jet, when the high energy particles, basically electrons are coming, there is also a magnetic field in that. So you can see this cartoon. So this is this electron is moving in this one, and because there is a magnetic field in this one, so in magnetic field, electron will spiral. And because of the spiraling of this one, then this will start emitting photons. Okay, so these arrows are the photons, emitted photons. So they will emit. So in some specific energy, like this is the energy in x-axis, you can see this energy. So this will peak. So there is a peak in this one. So this is called the synchrotron peak, and this is purely because of the electron which is moving in a magnetic field, and this will produce this one. Now, what happens is that because that electron is coming, and they will produce a peak like this. Now you see peak like this, and they will come. Now, okay. Now you see here this one. Okay, this one is because you see every electron is producing like this, and then this line, what you see here, this is a power law. This is a power law which is proportional to nu to the power alpha, whatever that may be. Okay, that is not important now. But you see, this is the low energy. This is little higher. This is little higher, and this is the higher energy. So this is this line what you are seeing. So this goes toward the higher energy end. So these electrons are producing this first peak. So then the higher energy one which are there, they are also still going. Many of them they will produce, but many of them they will not also produce. Then what happens that these electrons which are there, they are higher in energy. What they will do is that now the photon which is there, because they are moving in this medium as a whole, they are moving. So they will interact with these photons, mostly these photons. Then basically what they do is that because these electrons have higher energy, and they will kick this photon out. It is like this electron is very high energy electron is coming, and this photon which is here, this peak, this region, they will kick this photon, and electron will lose energy, but photon will be boosted in energy. And this boosted in energy is called the inverse Compton scattering. And this whole spectrum is called the spectral energy distribution is set. Okay, so this is the whole one is called the set. And now this electron will give energy to this photon, and this peak corresponds to this peak, because when the electron is hitting in this region, then they will boost this photon energy, and this will produce this one. So this is the traditional spectrum which is seen in almost all the active galactic nuclei or Blazar or whatever you take. Okay, so we see these two things. Okay, so this is the one. Now, what happens? Sometimes we have seen a third peak here, which is in higher energy, not in lower energy, but in this region. And it is very difficult to understand why this is happening. Well, you can always tell, well, this electron is still higher energy, then electron will kick this one and produce third one. Well, it is a nice guess, but normally it never works. Normally it never works. So there is something more to that, and that is what we are going to study, because there are a lot of investigation going on, and we really don't know whether this is because of this, again, neutrino, the electron being kicked out or not. But in many cases, we have seen that that is not going to explain all these things. There are a lot of difficulties in that one. So that is what we are going to study, these third peaks. And if we understand the third peak, we can understand many things. It will relate to a lot of observational consequences. Like, for example, now we have a lot of detectors on Earth, even in space. So all these things are looking for many of these signatures, which we are going to study. Okay, now, sorry, there is another thing called that in the third peak is coming. It is not like these two peaks are always there. Okay, always there. Maybe little bit left, little bit right, this will shift. but it is always there. This third peak sometimes come from some object, sometimes doesn't come. So that is not permanent. So to understand that, basically that is called flaring. Flaring, you must have heard of the flaring in the sun. Every 11 years there is a cycle. So sometimes the sun becomes very intense and it produces extremely powerful light. Even gamma rays, it produces all these things. So you see, imagine these objects, those who are millions of billions of times much more powerful than sun. So their flaring can be tremendous, tremendous. So that is what, I mean, just for a comparison, I am telling you that. So you see, this is the sun which is flaring. It is intense eruptions. And if you scale that 1 to million times, you can imagine how powerful this will be in these blasters and all this. That is what it is producing. And during that, it will produce so much of intense energy, so much of powerful gamma rays, cosmic rays, neutrinos. So that is what we are going to study. And to study that one, like for example, I am giving an example of this one. So this one is this one is this red one, but something which is in this one is suddenly it comes because of the flaring, and it can stay for a few minutes, it can stay for a few hours, it can stay for weeks, it can stay for continuous for a few months, but it will not continue forever. These are transient, okay? Okay, now, so detection of high energy particles. Okay, now we are talking about gamma rays, so let us talk about gamma rays. These gamma rays, whatever is coming from that source, it simply doesn't come to your detector. It is impossible. You cannot see them like that. So there is a way. Suppose, for example, this, let's say this is a photon which is coming, extremely powerful gamma rays which is coming, and it comes to the upper atmosphere. It will heat the atmosphere like nitrogen, oxygen, whatever that. It will interact with them. And because their light is so powerful, they will simply smash. So smashing that atom, it will produce a lot of particles. Again, these particles, they are still powerful enough. They will interact and they will produce showers. So this shower, where here suppose one interaction comes, and if you come below, let's say 100 kilometers or 50 kilometers, then you see it has spread to few hundreds of thousands of kilometers. So this is what it is producing. Now it is producing a shower. And if you are fortunate enough and you have a detectors here, it will detect these showers. And from this shower, it will reconstruct the direction and energy. With, of course, there are errors, and it will tell from which direction it is coming. Okay, that is the one which we detect. So there is no direct way that 100 tera electron volt, 50 tera electron volt, one photon is coming, or a high energy particles is coming and directly it will hit to your detector. No, it never happens. It is almost impossible to detect them directly, but they will either hit here or hit on the earth and produce a lot of showers. These showers we detect. We cannot detect the primary particle. Okay. To be more precise, this gamma rays comes. You see, it is producing a cone, and it is producing millions of particles, millions of low energy particles, and these particles will come, and this is your detector. This is your telescope, high energy telescope. So this will capture the light, and then it will reconstruct and tell from which direction it is coming and what light it is coming. Okay, so to detect these high energy gamma rays, there are telescopes. These are not the normal telescopes. These normal telescopes only see optical observable light, but these are very high energy one, so we cannot see them. So there are telescopes for that one. One is called HEGRA, high energy gamma ray astronomy, which was there in La Palma in Canary Island, Spain, but now this has been upgraded. It is called MAGIC telescopes. MAGIC. Okay, this is the one. Then second one is called HASTE, high energy stereoscopic system. It is in Africa, Namibia, So you can see what is, for example, MAGIC telescope has energy limit from 30 giga electron volt to 100 tera electron volt. This is the energy they will detect. So there are two telescopes. Then here it will go from 0.03 tera electron volt, well 30 GeV again from 100 GeV TeVs, and Veritas is in Arizona. Again, this is the one which can detect. And we have this is the newest one. This is called HAWK, High Altitude Water Cherenkov Detectors. It is in Mexico. It is near Puebla, Sierra Negra. So this is the telescope which can detect between 100 GeV to 100 TeVs, and this detector is completely different from this type of detectors. I will show you some of the figures. This is the MAGIC telescope, how it looks like. You see such beautiful sky. Well, all these telescopes, at least up to, not HAWK, not the Mexican one, but all others one, they only operate in night when there is no moon. If there is moon, then it cannot detect. Well, maybe it will detect, but it has a lot of problem. So this is, you see, a beautiful night, and they will detect high energy gamma rays when they come here. Okay. Then this is the Hess telescope. You see the size of the Hess telescope and size of your tower in Pisa. So this is the size of that one. Then you go to Veritas telescope. Veritas telescope is also extremely big. Then finally we will come to the HAWK telescope, High Altitude Water Cherenkov Detectors. This is the detector which can really operate day and night. It doesn't matter, but all the above telescopes can only operate in moonless night. Moonless night. If there is a moon, then there will be difficulties in detecting. But this is the telescope which are basically water detectors. Water tanks are there, and when these high energy particles will come, their secondaries will come, then they will hit this, and from here they will reconstruct. Okay, so this is the one which we have in Mexico. Okay, so these two peaks which I was telling you, this is coming from the electron in the magnetic field, and this is coming from the electron kicking this photon out to this peak. So these are basically, electrons are called leptons. I don't know whether you know or not. Electrons are called leptons, protons, and protons, neutrons are called hadrons. So these are the leptonic models because leptons take part in this one. Now the third one, which is I am putting question mark, is whether it is leptonic in nature or hadronic in nature or both in nature. That is what we are going to explore. Okay. Now, so normally what happens in all these things, whatever I was telling, the low energy radio to optical emission from the non-thermal synchrotron radiation, basically, well, I mean, it is better I will tell that. Basically what happens is that in these, the nature of the jet is such that the particles are being accelerated when they are coming out from the black hole. They are pushed out so powerful that because they are accelerating and they are producing this one, so it is there. Okay, so that we have understood very well. This is extremely well understood. This is well understood, not extremely well, but there are still some little confusion of this one, whether this is from the inverse Compton scattering or this is the external Compton scattering. So there are both contributions, but we understand fairly well this one. Okay, this one is still a debate going on. That is where we are proposing what are the things. Okay, now, so just to show you how the third peak looks like, this is a third peak. This is the third one. This is the third one, and first, second I have not shown. So these are the things which we have to understand really what are the mechanisms which are going on, and these are the energy, extremely high energy, extremely high. Okay. Okay. Now, as I told you, extragalactic background light. You see, when the star formation, galaxies formation took place, they are producing these photons. These lines are photons. they are producing this, and when your high energy photon is tera electron volt photons are coming, they will hit this photon and produce electron positron pair, and that's why their energy will be lost. So if you see the spectrum of this photon, how they look like in terms of wavelength, you see this is very high energy gamma rays, they are their background. This is X-ray, they are there, and this is UV, this is infrared. This is basically called the extragalactic background light, which we are interested. And this is the microwave, which is coming because of the Big Bang. After the 80,000 years of Big Bang, this is the one which is coming, and their number is very plenty. It is everywhere, even within you here, everywhere it is there in darkness, everywhere it is there. And if you see in terms, this is in terms of wavelength, this is in terms of frequency. If you see this cosmic microwave background is a peak, and this is the region where we are interested, because this is the one which is more important to detect this high energy gamma rays which is coming. Okay, so one has to really understand very well, at least to model how we are seeing that. Okay, how it normally happens. Suppose you have the high energy gamma rays coming from this jet, and this is the background light, EVL light. They interact, they will produce positron and electron, and that is the one which will lose energy. Okay, so how it again, now if you see the red shifts is the measure of how far this object is from us. Okay, so these are quite far objects, very far. Okay, now you see if it is very close to us, then if you see the energy, we can see up to 10 tera electron volt or little above that one. But when the redshift increases, the energy you will see will be decreasing. Okay, so energy you will be seeing will be decreasing, and now you see when the redshift is, let's say, 0.4, now you can see mostly energy up to 300 giga electron volt, not more than that. Well, I mean, you will be able to see, but the probability of seeing them will be drastically low. So if you go beyond that, then seeing the high energy photons will be very low. That is because all these photons, high energy photons which are coming, they will be absorbed on the way to produce low energy particles, low energy photons. Okay, now what happens? Normally, how these models works when you want to see the high energy particle. Normally, the protons are plenty there, so in the jet, so they are coming extremely high energy. Their energy is very high, okay, very high, and it is believed that, not believed, it is there. The photons are there in the jet, which I showed you. Let me show you. This is the jet here. There are a lot of photons are there. So when the extremely high energy, powerful protons are coming here, they will interact with the photon in this jet. Okay. Okay. These protons, they will interact. These protons, they will interact with the photons in the jet, and they will produce particles. So these protons can produce many things: neutrons, protons, pions. Pions is again a hadron, and this pion pi 0, it can produce charged pion or neutral pions, and these pions will decay. Neutral pion will decay to gamma rays, and pi plus will decay to neutrinos and electrons, positrons, and pi minus will decay to neutrino and electrons, like that. So they will decay, and subsequently they will come to Earth, and these are the high energy gamma rays that we see, or our detector will see. Okay, so this is the one which is there. Okay, so the reaction basically we propose. Well, this reaction is there. But we tell that this is the one which is most dominating in this nature. Okay, so proton plus photons, it is producing a delta resonance. This is again a nuclear particles. This is the particles which is produced, and this cannot stay longer. This will decay to proton pi 0, neutron pi plus. It can decay to again more particles, but that probability of producing more particles. For example, it can produce pi 0, pi plus, pi minus. So, but producing 4 particles, the probability is low, and here also it can produce more particles, but the probability is very low. So this is the most dominant one, and even the cross section of this one, cross section, you don't know, when it comes and heat a background, it will produce. So this is the one, how much area it will see, this is the biggest one. All others will be smaller than this one. So we tell that this is the most prominent contribution when it produces, and this pi will produce 2 gammas, you can see here. So this is the one which we see. Okay, so now from particle physics, if you do standard, very simple estimate, then you see what should be the energy of the proton, what should be the energy of the photons, background photons. So this is the relation. If you convert that to neutrinos, then again you will see what should be the neutrino energy, and again it is gamma. So these things you can see. Okay, so this is the one which how much energy they will take. Now, to explain this third peak, what do we assume? We assume that whatever is going on here, these 2 peaks, perfectly okay. We agree with this one. It is consistent. There is absolutely no change to this one. But during the moment it produces this one, something goes extra. What it goes extra? Some violent process, because naturally when you see the sun, the normal today, if you see, it is okay, so nothing going on, so it is a natural, let's say it is these 2 peaks. But something suddenly happens, we know that there is some eruption, maybe there is because of the tension in magnetic field, because of something happens. So that something happens, that is what we are going to tell, that really what we assume. Okay, now this is the model what we have given. We tell that during the normal 2 peaks, whatever you see, this is the jet, it is a cone which is there, both the cones, and this is the central black hole. Matter is going into this one. But when the flaring happens, a inner jet scenarios takes place. This inner jet means the intense process is going on. This is producing a jet within this one, which is hidden. Really, you cannot see this one. But that intense jet has a density of photon much bigger than what you expect here. Okay? And this is the place where your protons are, which are accelerated from here, base of this jet. They are accelerated and they are scattering here and producing these pions, and this subsequent decay of pions will produce the observed high energy gamma rays, or maybe neutrinos. Okay, so far we have not seen this neutrino. I am going to talk about if I have time. So this is the one which will contribute. Okay, I am not going to talk much mathematical details because it is of no use. I will just try to tell in a more in a way where you can understand. So this is basically a power law which I was telling from the beginning. It is a power law. Power law looks like this. This is the proton energy, and power law goes like e to the power minus alpha. When you plot this one, it will come like this. It decays like this. Okay. So in energy, and it is the flux, so it will decay. Okay. So this is the one we assume, and then we assume that when the proton is coming, it will interact with these background photons and produce these pions. But for that, one has to calculate what is the optical depth. Optical depth means how far your proton can go before scattering or before losing energy. That is what it is related to. Okay. And then from this can be calculated from observable things, so which I am not going to talk about. And once you have that, now normally what happens is that, as I told you, you remember when in this inner jet, this small one, which is this small cone, this is the place where photon has high density, and we don't know. Really, there is no way you can directly know. So we have to assume something. What we assume is that suppose you have an energy of a photon which is coming, let's say energy is E1, okay? Energy is E1. So photon with energy E1 here and photon in energy E1 here, okay? And photon in energy E2 here and photon in energy E2 here. If we want to calculate what is their density, so the density of photon here is much higher than density of photon here. So, but if we take the ratio of photon density energy E1 to photon density at energy E2 is approximately equal to photon density at energy E1 and photon energy at energy E2 here. This is the assumption we take. So that, because we know what is the photon density here, so we don't know. So what we take is that the ratio of this one, the unknown one, can be expressed in terms of the known one. So that is what we are assuming, and that is the only assumption which we have to proceed further. So once we have, then we are through. But now, again, in particle physics or quantum mechanics or wherever you go, or even in classical physics, if you see the number of particles, what you see, number of photons, what you see, they will be proportional to the number of protons they are coming, because proton is hitting to the background. So if the number of protons are hitting to the background is more, then you have a lot of particles output. And if the density of particles in the background is more, also it will produce, because if you have very less number of particles, let's say, for example, you are going from your house to your college. So if there is nobody on the road, then probably you will not meet your friends. Maybe you will not see anybody. But imagine that it is in a fiesta day. Then when you are going, you will see a lot of people. So probably you may see some of your friends there also. So it is like that. If the density of particles are more, it is highly probable that this proton will interact with them, and you will produce this high energy gamma rays. But if the density is low, then obviously you are not going to interact. Similarly, the same happens. If the high energy protons number is more, then there is a high probability that it will interact with the background photons. Otherwise, it is again low. So it is just proportional to the product of this one. Okay. So now if you take that and do some calculations, and this is the one which I was telling you, this extragalactic background light, it will reduce your flux. So this is the observed flux, what we see on Earth, and this is the intrinsic flux of the object. Imagine that in between the source and your detector, there is nothing. It is complete vacuum. So then this factor will not contribute. This is exactly 1. This is exactly 1. Okay, but because it is there, it will reduce. So this is intrinsic in the sense that suppose nothing is there in between the source and the detectors, how the flux will behave. That is what it is important, because this is the one which will tell about neutrinos. Neutrino is the particle that I told you. It will really, it is almost invisible. Well, it is invisible, of course. Almost it doesn't interact, but this is the particle, almost no mass. This is the most terrible particles nature has so far produced. This is the most elusive particle. So if we understand these particles, then we understand a lot of things about the universe. Okay, so to calculate that, we need this one. That is why the intrinsic flux. Okay, so now what we do is that the density, I told that energy E1 and E2, they are naturally related to flux with energy E1 and E2, but that energy, what I was telling, the background energy, and this energy which I am talking is the energy what we observe on Earth. Okay, so their flux at energy E1 and their flux at energy E2 is related to this. This is the observation, in left hand side is the observation, and this is the one which model gives. Okay, so this is our model what we find. So if you relate that one, then you understand that. Now this one has to be calculated taking different models, because people have given different models of our extragalactic background light, and these are very complex things, so we have to really rely on them, and they are very reliable. Okay, all right. So by doing that one, then intrinsic flux looks like this. You see, this is this alpha is the power law for the proton, and this is a +3. So you just remember that one. Okay, that is the one. So otherwise there is nothing to tell there. Now I will tell you using this one what we get. Okay, so this is results. Some of the results I will not give you most of them because there are enormous amount of result which we have generated. So you see, these are the third. This is the third peak which we saw, and this is our model. Okay, it explained extremely well. So if you magnify this one, this looks like this. This looks like this, and this is our model. And these two are some other models. These two are some other models, and our model is much better than that. Okay. Now let me go to another one. This is another object, 1ES 1959 plus 650. It has eruption, which was observed on 4th of June 2002. So this is the data they give. And this is the model, which is this black line, solid line, what we give. This is the model, what we explain. If you see that, the whole spectrum 2, and this is the one which we give. Okay. These are all published papers. So, okay. Then there is another one called Markarian 421. This is another Blazar, high energy Blazars. So it had an eruption in April 2004. Again, this is the data, and this is red one is our model. If you see here, again, I am giving these two, and this is the one which we give. Let me put little more. Then another one which was erupted in May 2009. So this is their data. This is our model. What we explain, and here again, okay. So to be more precise, you see this black line is our line. This line, this red line is the one which is telling that suppose you have nothing in between the source and the detector, then we should see this one. But it is there, so light is there. This background light is there, so obviously you will not be able to see. This slowly goes down. You can see when the energy goes up, then their flux goes down. After some time, you will not be able to see. Okay. So these are the things. Then there is another one. I think there is no point in discussing about that one, but I can show you. You see that this is the data points, and this is our model. You see, it is very good. Okay. So we have used this one, and we can get this. There is another one you see here. These are the data points, and we show that how we fit. Well, there are details which there is no point in discussing about details. And again, you see, this is the data points, and we are explaining this. You see extremely well. These are the errors in this extragalactic background light because there are some uncertainties. They have put this one. So within that uncertainty, we can get the central values very well. Okay. Now, so this is all. Well, there is another one. Maybe I will tell you. So sometimes in 2006, some people they claimed that one of the objects which was emitting this high energy gamma rays flaring, it was looking like this. So they saw that. You see that it is like a sine wave. Okay, it is like oscillating wave. So this is they are showing from both these objects, two objects. What we showed is that using our model, we showed that it should go like this, and this is the data, and this is our model predictions. Okay, so this is the one which we have explained using this model again. So there are many more which I have put everything. I mean, most of the things which you can see, we can explain very well. Okay, so these are the things which we are trying to explain, because more you explain, more objects you explain, then you know that what you are telling is probably correct. Okay, there are other interpretations also, but because we are trying to explain so many things, and recently 2019 we have explained in one of the most important papers, we have explained 42 explanation extremely well. Okay, so which of course I don't have that here, but this is the explanation what we have given. Now, if you have this, then as I told you, if these objects are producing high energy neutrinos, sorry, gamma rays, they should also produce high energy neutrinos. Then what is the advantage and disadvantage of that? You see, if you are producing, say, high energy protons, then because of the magnetic field, this will deflect. So suppose you are here, so this will deflect. Maybe then something is there somewhere else and it will come from you here, but that may not be from this object. It can be from somewhere else. Or if the proton is extremely high energy, extremely high, 10 to the power 19 electron volt, this will not be able to come because this cosmic microwave background interact with cosmic microwave background and lose energy, so nothing will come. Photons, they will be absorbed on the way, they cannot come. So high energy photons cannot come, okay? Very high energy. So even these high energy photons which we are talking about, above few TeVs, tera-electron volts, they will not reach here. So you cannot see. The only thing which will reach to the earth is neutrino, because this particle is so devil interactions, they will simply come straight to your detector. Now, question is, can you directly detect these neutrinos? Answer is no, you cannot, because you can detect directly these neutrinos if they are coming from sun or supernova, which is comparatively low, very low energies in this case. But if they are high energy, there is no way, because these particles, they will pass through earth, hit the rocks in the earth, then they will produce a lot of particles, chubascos, and then that chubascos will be detected by the detectors. There is no way you can detect again this extremely high energy neutrinos. Okay, so this is something very interesting. Now you imagine that you see some high energy gamma rays, not very high, because very high it will be absorbed, very high energy gamma rays, and then you see neutrinos that from the same source. Then you see that there is something interesting going on. So you are seeing two types of messengers from there. Okay, that is what is now interesting. Now, as I was telling from the beginning, so to see a extremely high energy protons or extremely high energy neutrinos, to produce that, you need a accelerators. You probably, most of you must be knowing that there is a place called CERN, Center for Nuclear Research in Europe. It is in the border of Switzerland and France. This is a 27 kilometers diameter. This is the accelerator where particles are accelerated to very high energies, tera-electron volts. But to produce these tera-electron volt photons, you need an accelerator to produce 20 times of that energy. So we have absolutely no technology, no place, no idea to produce that. The particles which we are seeing, you need a accelerator of diameter, something like the diameter of our solar system. If you have an accelerator of diameter of our solar system, then you can produce such a extremely high energy protons. So then we are helpless. We cannot do anything. So unless we depend on natures, we cannot do anything. So our research is over. So that's why to produce this, to detect this extremely high energy neutrinos, this is no more a source. You can do nuclear research, you can do particle research, very good. But beyond that, you cannot produce this. So you have to depend on nature. So we have to have detectors on Earth to detect these particles, and these detectors need to just look. Okay, if we are fortunate enough, we will get this. And these extremely high energy particles, 10 to 18 electron volt, 10 to 19 electron volts, they will come and hit your detector once in a century, once in 100 years. So that means if you just put one small detectors and sit there, maybe you have to sit for 100 years so that one will come. So what we have to do is that, well, let us take 100 detectors like that and put in a region, so we can wait for 1 year. Or if we are still multiply 365 times to that, then you can wait for 1 day, maybe you will get a signal. So that is why Now, to detect these particles, you need enormous size detectors, like size of Mexico City detectors are there. They are this water tank which I showed you in the Hawk telescope in Mexico to detect this. So there are detectors in Argentina that is called Pierre-Roget detector, which is 3,000 square kilometer detectors. So they are looking to the sky to see these signals are coming or not. Okay, so these are the one which is important. Now to detect these neutrinos, we have special detectors in South Pole, and there are others which are coming in Mediterranean. But the South Pole one is interesting. That is called the IceCube. Okay, which I am going to talk about. And this IceCube, well, recently in 2017, 22nd of September 2017, this IceCube detector saw neutrino signal of 290 tera electron volt, and at the same time they saw a Blazar which was emitting in very high energy. This is flaring. Okay, basically this Blazar name is TXS056 plus 056. These are some names given some catalog, so you don't have to worry about it. This is name like Rodriguez, like Sarida or whatever that. Okay, so these are names. Okay, so these objects was, if you see their redshift is 0.3, means few million light years away from us. So this is the object they saw that time. It was producing extremely high energy gamma rays, and they saw that it is coming from the same coordinates. So they saw that maybe this is the object which is responsible. And there is another one they saw in, this is a paper published in 2016 Nature. They also saw a extremely very high energy neutrinos, and close to that one they saw some object was flaring. But this is this object is not very sure, because this is something the error is little bigger. Okay, so but irrespective of whatever that may be, so I will not talk about this one. Then let me talk about these neutrinos, how they are detected. So please tell me when to stop. Maybe I will take another 10-15 minutes to finish this one. So this is the neutrino detector. This is in South Pole. You see, this is between 50 meters below the ice up to the almost 3 kilometers. So this is the detector region. This is the detector region. You can see, and to construct these detectors, it has, well, these are the let me show you. These are, you see, these are these lines. What you see, these are the steel strings which are hanging within this ice. Okay, and each one is hanging in this ice, and these are detectors. These are called photomultipliers, but special types. One of them will cost something around $10,000 to $12,000. So they are 5,482 digital optical modules are there. So you can imagine that how much cost it will be. It is taking all these things into account, even in going to South Pole, drilling the hole and everything. It is something like $280 million, which was used, and more than 300 members with 48 institutions and 12 countries participate in this one. Okay, so by the way, Mexico is not part of this one. So this is the detector looks like. Now how the interaction takes place. Suppose you have a signal coming from somewhere else, let's say from other side of the, because normally it will come either from the side of the earth or from the below the earth. It will not come from the top, because top one, the matter is so less, is simply that will penetrate through. Okay, so when it is coming, it will produce showers. You see that all these different colors you are seeing, they are the triggering of this optical modules, these footballs what you saw. They are producing that, and then directly once they get the signal, that signal will come to the space, and that directly that will telecast, well, not telecast, that will send to the center, where they can, it is a real-time events. Probably they can all keep this data. Okay, so there are two types of events. That is, one is called shower, another is called trek, but that is not important now. So how they look like. So when this signal, this neutrinos will come, hit the rocks, then they will produce secondary particles, and these secondary particles, they will produce all these photons. Okay, finally they will produce photons, and also they will produce electrons and muons. So these electrons and muons, when they are passing through the ice, they will produce one type of light called Cherenkov light. That is only possible when the refractive index of a material is greater than 1. Okay, so ice has greater than 1 optical this refractive index. So this is the place where it will produce. Now you see, when you see the electron, this red one it is producing, you see it is going zigzag. Okay, so you see it is going zigzag, and if you see the transversal cut, it looks like a diffuse circle. But for muon, it looks like exactly circular because it is going very straight. So this is the one. From there, by seeing these, they can tell whether it is a muon neutrino or electron neutrino. And tau neutrino also will produce similar. Sorry, tau neutrino will also produce similar this one, like electron. So basically, muon neutrino and rest of the neutrinos, you can see. Rest of the neutrinos means not something which is sterile neutrinos, not something which is not standard. I'm not talking about that. I am talking about standard physics, whatever is known. So from these things, they can really differentiate between the muon neutrino and rest of the neutrino. You see here how it looks like, So this is the one which you can see. So this is a real-time trigger they have seen, and they have generated this. You see the particle is neutrino probably hit somewhere else here. Then it is coming, and this signal, the particles which are coming, they are producing all these photons, and these are triggering to these optical modules, and they from there timing and which direction that is moving from there, they can see from which direction the neutrino was coming, from where it is coming. So although it is complicated things, but it is, I mean, this is the way it is done. Now they have seen so many events. Now you see, this is a low energy. These are the events they have seen, neutrino events, but there are still not many events here. And they have also seen sources, whether there are any sources correlation with that one. But most of the cases, it is very difficult to see. It is very difficult to see from where they are coming. And so this object which I told you that in 2017 they saw, this is the object which was flaring in high energy, and these are the neutrino events they calculated. So using our model, we tried to estimate whether we can do that or not. And to estimate that, so this is done. This is the work which we did with Carlos, who is also from Merida. So this is the one. This is the data which is observed in high energy gamma rays, and this is the model what we give. So we explain very well. And also this another event what I told you that we had seen. These are the two events we think high energy gamma rays. We think that it is coming from there, and we try to feed that one. So we can feed this, and this is the neutrino event here. Neutrino, it should give flux of this much, and this is the neutrino which should give flux of this much. That is what we have. This paper is in referring. Maybe in 1-2 days we'll get the results, what they tell. Hopefully this is almost accepted, because we have already given the response to referee, and it is already 12-15 days we are waiting for that. Maybe in this week we will get something. Okay, so this is the one which is coming. Now this is not important now. Okay, to summarize this, so basically what happens is that the flaring events, which the multi-TeV flaring events which are coming from all these blazars, high energy blazars, we assume that there is this type of reaction, proton plus gamma goes to delta plus and is decays, and this is the one which is producing gamma rays which we observe, and this will also produce neutrinos, but unfortunately these neutrinos are very low energy. So in future, if we have a detectors of let's say 5 to 10 tera electron volt detectors, then probably we will be able to see. But again, because these objects are very far away, their flux will be very small. Okay, so this is very difficult to see, but at least for these gamma rays. Now, if we want to detect these high energy neutrinos, which is already done in IceCube, then probably this scenario will, well, the reaction will be the same, but the region where it is interacting will be difficult. And will be also different, which we have already shown here. But the problem is that from one neutrino, it is impossible to tell anything. So one has to really wait longer, okay, so that one can see, okay. So this is the summary which I have. And now to tell, before I finish this, I am thankful for this online seminars, and also students, those who are participating in this one, those who are listening to this talk. And now I have proposal that students, those who are interested to do licenciatura, maestria or doctorados, they are very welcome, because we can have licenciatura, for example, you can have licenciatura where we can, maybe some of the financial support will be available. But to do maestria and doctorados, you really need to come to UNAM, participate, and then in this entrance examination, pass that, and you can do that one. So recently, well, something more interesting, we have just published that it was accepted 3-4 days ago, and 2 days ago, Carlos again submitted the proof copy. So there we are claiming that even with this model, you can explain the high energy gamma rays from gamma ray burst, which are the most powerful explosion after the Big Bang. So we could explain this. So this is something very interesting, and these fields are supposed to be most interesting all over the world. And unfortunately, we don't have many people in Mexico, so I will be happy if people can come and join here and do research and do some interesting work, which will be useful for the country as well as for the students, okay? And finally, thank you very much. Hello?
Yeah.
Okay.
Thank you very much, Professor, for your talk. Since like I told you before, we have like a delay of like 15 seconds. So right now there's a brief space for questions. So if anyone in the audience has any questions, either in English or in Spanish, you can ask them. Así que ahorita iniciamos un espacio de preguntas disponible para la audiencia en línea. Pueden preguntar a través de los comentarios en Facebook. Pueden preguntar tanto en español como en inglés. Okay. So we will start with a few questions that we received earlier in the talk. First question. If blazars, quasars, and radio galaxies are the same object, why should they have different names?
Well, I told you, because it is the angle through which we are seeing, how much we are seeing. For example, okay, let me go to the okay. Like for example here, if we are within this cone, that is called Blazar, because the Blazar is the name where any, suppose there is some variation in flux or whatever that. So immediately you can see here. So that is the name, it is called Blazars. And you can see even in terms of few minutes, half an hour, if there is a change, you can see. But if you are here, that cannot be seen. Also here, it is, you are within the cone, so any variation can be immediate. But here you may not be able to see this. Also the particle interactions, you may not be able to see lot of signals here and even less here. So depending on this angle, you can tell it is classified. So that is all. So I mean, there is nothing more to tell about these things. This is just a classification, depending on which angle you are, where you are. It is like, let me tell you a story. If a person is blind and he, from his birth, and he doesn't know how the elephant looks like, so if you tell him what is head, what is tail, if you understand, then if you take him and tell him that, tell him to touch the head of the elephant, then he will tell, then ask him how is the elephant looking like, he will tell it is a big object, it is like a big round of. If you tell him to touch his ear, then he will tell it is like a palm leaf. If you tell him to touch the tail of the elephant, then he will tell elephant is like a rope. So it is like that where you are standing. There is nothing to do with. Everything is the same, but it is just where you are standing and what you are seeing.
Okay, thank you. Next question. This phenomenon of blazars and quasars, these emissions, these jets, do they appear in any black hole or in any galaxy, or do they have to have certain characteristics?
No, the jets are almost everywhere. Anywhere where there is a intense activities, enormous activities going on, there is a jet. So actually two jets, because one jet is not stable, so it cannot produce. It has to produce two jets. So yes, most of the cases, almost all the places where there's central black hole and mass is accreting into this black hole, this is form jets. Whether it is small, whether it is big, whether it is powerful or it is less powerful, it will produce. It is invariably it will produce a jet.
Okay, thanks. This next question is okay, about the IceCube detector you mentioned.
Mm-hmm.
There are two questions actually. We could combine them in one question. First, it says, which other, is it only geared towards neutrino detection, or what other kind of I don't know, function or detection could it do? And the next one is, is it made of ice and not any other material?
Okay. Well, second question. Yes, it is made of ice. Is most, because now question is that probably I can refine your question. Why do you choose North Pole, South Pole? Why North Pole, not North Pole? South Pole ice is very clear. Mostly it is not contaminated. You know that we are contaminating so much. It is quite pure, transparent, and they have studied, because as I told you, the refractive index of this one has to be very specific. So if there are contaminations, then it is very difficult. One has to understand very well. So this ice in South Pole is very clear, and it is kilometers long depth. So that is, so this ice acts as the detector material. Okay, just a minute. So the detector material, and when this muon or electron pass through the ice, this blue, this shaded regions, what you get, this is the one which is produced. These are the photons which are produced, and this will be captured by these detectors. The strings where we have put these optical modules, they will capture this light. This is this optical modules where these round things, they will capture this one. Okay, they are, well, if they have put the color depending on when they are triggered. So this is the one thing, and so it is purely ice, because that it doesn't cost much. Otherwise, if you want to make a IceCube detector like the one which we had in South Pole in Mexico, so yeah, you imagine this is 1 kilometer cube, so 1 kilometer depth, 1 kilometer width, 1 kilometer wide. So this is how much money we have to spend just for ice. You can imagine that. So this is a natural one. And the first question, what is the first question? Sorry, I forgot.
If this device can only be used for neutrino detection, or if it can have any other use?
Yes, normally it is purely for neutrinos, only purely for neutrinos, because this is the one which can detect neutrinos. For example, it can differentiate between muon neutrino and rest of the neutrinos. Okay, so this is what I understand, and so far I don't know you can detect any other things. But from here, the detection of this one, you can constrain, for example, dark matters and all other things you can constrain. But for detection, so far detection is concerned, it is purely for neutrinos.
Okay, we have another question. It reads, if we have students here who are interested in this line of research, which kind of like courses would you recommend to take? For instance, which particle physics courses or which mathematics courses that would come in handy for them?
Look, this is, as I told, this is astroparticle physics. So one has to know little bit of astrophysics, one has to know little bit of particle physics, and so these are the things which are necessary. And one has to know also little bit of nuclear physics. So there are many things involved in this one. But what I suggest is that if somebody understands particle physics from a fundamental level, it is not very deep, fundamental level, and quantum mechanics up to some extent, then astrophysics, of course, one has to know, but for specific things, one has to know specific things, okay? It is not that everything he has to study. So little bit of many things one has to know. So what I suggest is particle physics in the fundamental level, quantum mechanics some extent, and neutrino physics, maybe neutrino physics up to some fundamental level is necessary to do this.
And what about mathematics? Like special mathematics courses, like, I don't know, tensor analysis, complex variable calculus, for instance?
Okay, you see that if you, I mean, quantum mechanics, if you try to study, you have to know complex analysis, because without complex analysis, quantum mechanics you cannot study. So complex analysis is a necessary thing to know, because quantum mechanics is basically application of complex analysis, because wave functions and all these things are their complex functions. So one has to know. Then other things probably you have to know is that differential calculus, because differential equations, again, Schrodinger equation is a differential equations. So one has to understand the differential equations. Then what else? Well, I mean, normal basic mathematics, like for example, whatever is taught up to the undergraduate level, and complex analysis, I think it is sufficient enough.
Okay, thank you. Next question. What is important about the detection of neutrinos? What importance or what impact in science could it have?
Okay, as I told you, neutrinos, because you like the, cosmic microwave background we have detected, then we know this tells that this Big Bang was there. Now, during the Big Bang, during the cosmic microwave background also, there are neutrinos being produced, and their neutrinos are there everywhere. Suppose tomorrow we detect these neutrinos, then it will confirm that cosmic microwave, this Big Bang theory, okay? Another thing is that these neutrinos, because now there are so many reactors and everywhere accelerators to study these neutrinos. Neutrino is one particle which is very, very, very peculiar, because this is the only particles probably we know, apart from some other complex things, that they are oscillate. Oscillate in the sense that neutrino is not like electrons or protons. They are not, when you produce electrons, it is electrons, pure electrons. But neutrinos are not like that. They are some complicated superposition of 3-4 type of things. So whenever they propagate, and wherever you see, you may see here, suppose if you are detecting it is electron type, somewhere else you will see muon types, somewhere else you will see tau types, somewhere else you may see something else. So this is the particles. If we understand the properties of these particles very well, then we understand many things. For example, say if you have the nucleosynthesis, nuclear reactions going on in stars and all these things, we don't know anything about this one, then you cannot tell definitely what is there in the sun. So to understand these neutrino properties, it is very important to know what is going on in the sun, what is the composition of the sun. All these things are very important. So it is basically to understand the fundamental constituents in the universe, and to understand the nature of, let's say, solar nuclear reaction in sun and all these things. So this is a basic things for our understanding of nature in the very fundamental level.
Okay, thank you, Professor. We have one last question. It reads, we have what are the conditions necessary for the detection of neutrinos from the photohadronics process in terrestrial detectors?
Well, for example, look, neutrino detectors are very, it depends on energy. For example, if you consider the nuclear reaction in the sun, it is producing mega electron volt neutrinos. So we have detectors like, for example, detectors in Japan, which is called Super Kamiokande now, or maybe it has upgraded to Super Kamiokande. And there is another detector in Canada, which is called Sudbury Neutrino Observatory. So these, because they are MP neutrinos, mega electron volt neutrinos, basically not very high energies. For them to detect, you have specific conditions. For example, they will come, they will hit, because they are water detectors, so they will come, and when they will hit the electron in the water or proton or neutron in the water, depending on normal water or heavy water, so then they will produce signals, and then these signals are being detected, or they will produce Cherenkov light, so we will see this one. For this particular one, if the energy of the neutrino is increased, then your detector type is different. For example, if it is a photohadronic interactions, and if you want to see these neutrinos in IceCube, IceCube will not be able to see any neutrinos from sun, because the solar neutrinos is very low energy, and this has a lower limit, something like 10 tera electron volt or little less. I don't know exactly now they have upgraded or not. So they are completely different types. Now these neutrinos to see extremely high energy neutrinos, it is the same photohadronic interactions, but their background photon is low energy and the proton energy is very high. So this can be seen in IceCube. There is no problem. Only thing is that we have to produce sufficient amount of neutrinos so that their flux is not very small, which we will be able to see. Even 10 TeV, 20 TeV neutrino can be seen, but unfortunately their flux will be so low, it is almost impossible. So there is, you don't need any extra technology for that. Only thing is that their flux has to be high, and that is all.
Okay. So for now, we don't have any more questions. Okay. So we end up here. So thank you very much, Professor, for your time.
Thank you very much.
For accepting with us to share some of your line of research. And thank you to all the audience that have been watching this talk all along. Everyone was very, very interesting. Now let's say a brief farewell in Spanish. Bueno, muchas gracias a toda la audiencia que estuvo viendo esta charla hoy, y muchas gracias al doctor Sahu, que nos acompañó y nos brindó su conocimiento durante esta charla. Entonces, no nos queda nada más por decir, simplemente queden al pendientes de las siguientes actividades que organice la Asociación Estudiantil de Ingeniería Física, y muchas gracias por vernos. Hasta luego.
Ok, gracias.
Por nada. So, Professor, if you could wait only a few minutes.
Okay, sure.
Seconds until we go offline.
Okay.